Today we're going to talk about some techniques to find Taylor series in faster ways. And so it turns out that once you have a built-up family of Taylor series that you already know very well, then you can just use them to find Taylor series of related functions. And so here at the top of this paper are 4 common Taylor series that we've already seen before. And so we can use the Taylor series for e to the x or sine or cosine or 1 over 1 minus x to develop Taylor series for a bunch of other functions. And so the advantage here is that we don't have to take derivatives of a function over and over again in order to find its Taylor series if we can just relate it back to a different function that we already know. And so as an example, let's try and find the Maclaurin series for x cubed over 2 times e to the 4x squared. And so first of all, just to be clear, you could start taking derivatives of this function and plug in 0. But that would quickly become disastrous because taking even a single derivative of this involves both the product rule and the chain rule, and then it's going to be messy just to find the first derivative, and it'll get even worse to find the second derivative and the third, and so on. And so instead, we can break this up into pieces by using the fact that, first of all, there is an e to the something in here. And so I can start with my e to the x formula and then manipulate that to get the rest of it. And so what I'm saying here is if e to the x is equal to the sum of x to the n over n factorial from n equals 0 to infinity, then that implies that e to the 4x squared is the series when I just replace the x's everywhere with 4x squared. And so I'm just substituting this 4x squared in where the x's used to be. And so this will be a 4x squared to the n over n factorial. And then it will be helpful to expand this power of n right here out into the terms just so that I can separate the x from the rest of the stuff. And so in this case, using the power rules, that would be a 4 to the n x to the 2n, and then still divided by n factorial. And now the only other thing I have to do is multiply out this x cubed over 2 out front. And so I'm just doing this one step at a time so that I can more easily track what's going on. And so x cubed over 2 times e to the 4x squared, that's just going to be equal to the same sum that I had from before of 4 to the n x to the 2n over n factorial. And then I'm just going to multiply each of these terms by an x cubed over 2. And it'll be nicer if I sort of lump the x terms together. And so I just want to combine this term and this one into a single term inside the sum at this point. And so I'll have a 4 to the n times x to the 2n plus 3 over 2 times n factorial. And so that is the Taylor series for this function. All right, now let's look at one other way that we could manipulate Taylor series in order to help us. And so in this example, we're going to try and solve a specific integral to within 2 digits by using Taylor series. And so the thing to notice here is that if we had just been asked to find the antiderivative for sine of x squared, there's no easy way of doing that. Sine of x squared does not have a Taylor series, or sorry, it doesn't have an antiderivative that can be written down in terms of functions that we know. And so there would be no way of using the fundamental theorem of calculus here to help us evaluate this integral. However, it turns out we can use Taylor series to help us get a really good estimate of this integral. And so the idea, again, will be to start with Taylor series that we've seen before, which in this case would be sine of x, because that's related to something I can see inside this integrand. And so the Taylor series for sine of x, that one was a minus 1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial, where the sum starts at n equals 0 and goes to infinity. And so now if I want to figure out what sine of x squared is, then again I'm just going to replace all of my x's in the first series with x squareds now. And so that'll be minus 1 to the n, x squared to the 2n plus 1 over 2n plus 1 factorial. And so in this case, that'll be sum of minus 1 to the n times x to the 4n plus 2 over 2n plus 1 factorial. And so it becomes 4n plus 2 here just because when I have powers like this, you just have to multiply them together. Okay, now I'm ready to take the integral of sine of x squared. And the way you do that is I've got to just plug in my series here. So that's the sum from n equals 0 to infinity of what I just wrote down. And then it turns out that you can just take the integral of each of these terms inside here one at a time. And so, in other words, because I'm taking this integral with respect to x, the only term that I really care about here is this one right here, because the others are all constant with respect to x. And this term right here is just power of x, and so I can use the standard power rule for integration in order to figure out what this is. And so that means this would be the sum from n equals 0 to infinity. The minus 1 to the n stays there. The x now is raised to a 4n plus 3 because I have to raise that power by 1. And then I divide by the new power. And then I still have the 2n plus 1 factorial down there. And then it is the case that because I did integrate this, I would typically need a plus c. And so now if I want to figure out the integral from 0 to 1 of this, sine of x squared dx, then that just means that I'm going to plug in 0 and a 1 into this sum. And so let me write out the sum again. And then I'm evaluating this between 0 and 1. And so when I plug in 0 into this series, it is the case that all of these terms have some power, some positive power of x attached to them. And so when I plug in 0, actually the whole thing just disappears. And then when I plug in 1, all of the x's just become 1s, and so I can just drop the x term here. And so I do want to say that sometimes when you plug in 0, you don't get 0 for the entire series. The only thing that you have to be worried about is if there is a constant term in your series, or in other words, if there is a term that is x to the 0. Then when you plug in 0, that term will still be around. In this particular case, there's not a term like that anyway, and so it does go away. All right, so at this point then, what we've said is that the only thing that's remaining is the sum of minus 1 to the n over 4n plus 3 times 2n plus 1 factorial. Okay, so this should be the true value of that integral, but I want to approximate it to within 2 digits. And fortunately, you can see that this series here is alternating. And so that's very useful because that means that I can just write out terms until I get one that's less than the error that I am looking for. And so in this case, that would be until it's less than 1 over 100, because that would correspond to getting 2 digits correct. And so if I do that, then when I plug in n equals 0, first I'm going to get 1 over 3 times 1 factorial. And then when I plug in n equals 1, I'm going to get minus 1 over 7 times 3 factorial. And then if I plug in n equals 2, then I'm going to get plus 1 over, and then this will be 11 times 5 factorial, and so on. All right, and so if I look at this 11 times 5 factorial is 5 times 4 times 3 times 2 times 1, and so that would be equal to 20 times 6, or 120. And so this part right here is already, just the factorial part is already less than 100. And so this turns out then that I only need these first 2 terms in my approximation. And so I could say that this is approximately equal to 1/3 minus 1 over 7 times 6. And that'll be my final approximation here. So just as a quick recap, I was specifying that this term was less than 1 over 100, which means that I could stop the term before it for my approximation. Okay, so here we saw that it's really helpful to substitute into Taylor series, but also to integrate them term by term. That's still something you can do. And it turns out that we have a theorem about the relationship between Taylor series and a manipulated version. And so if you integrate a Taylor series or if you differentiate it term by term, then it turns out that the resulting series still has the same radius of convergence. And so in other words, it still converges for roughly the same values. The only issue is the endpoints on the interval of convergence. Those might change, but the radius itself and the inside of the interval does not. And that's the same story if you multiply or divide a series by any power of x, assuming that you divide it by some power, or after you divide it by the power, it isn't undefined. And so as long as the series is still defined, then it will maintain the same radius of convergence. And so in other words, it's saying that we can integrate or differentiate or multiply or divide by x without worrying very much for these Taylor series. All of those things are valid things to do.